Welcome to lesson 4 of AQA A-level physics, particles and radiation. Today we're going to focus on alternative decay mechanisms, Feynman diagrams and exchange particles. So let's get started. So the first thing I'm going to look at today is some more decay mechanisms. So in video 2 we looked at alpha decay and we looked at beta minus decay. Well, there is an alternative to beta minus decay, and that's beta plus decay. And in beta plus decay, a proton changes into a neutron compared to beta minus decay, where a neutron changes into a proton. So beta plus, a proton changes into a neutron. That means if we want to write out a general equation, we can do this. So let's start off our general format of nuclei notation. So X, as always, represents my element. A is my nucleon number and Z is my proton number. That forms another nuclide. X, the new element. A, the nucleon number, and this time it is Z minus 1 instead of Z plus 1. Because it's beta plus, this gives out a positron, which is the antiparticle of an electron, and this time, instead of an anti-electron neutrino, we get an electron neutrino. Let's represent their nucleon numbers and their proton numbers like that. So let's just pause for a moment. We've got a positron here, which is antimatter, which means we need a matter particle to balance out the lepton number. But we'll have a look at lepton number conservation in a later video. We've also got another decay mechanism, which is termed electron capture. Now, electron capture, the nucleus of the atom captures and orbits an electron. Hence, when we write this out, we get X, A, Z plus an electron this time, because it's capturing it. So this is on the left side of the arrow. And this time we form our new element. Remember, it needs to balance on either side. Well, if we've got minus 1 on this side and subtract, this means it's dead minus 1 here. But notice the change. This time we've got two matter particles, and that's because they're on either side of the arrow, meaning lepton number needs to be conserved, i.e. the lepton number of an electron is plus 1. The lepton number of an electron neutrino is plus 1. They're balanced on either side of the arrows compared to before, where both of your leptons ended up on the right side of the arrow. A common example of electron capture is beryllium-7. So let's just work through an example. So beryllium, nucleon number 7, proton number 4, captures an electron, just like that. So what can we do to work out electron capture? Well, mass number is 0 for an electron, so that's going to remain 7. We've got 4 minus 1 gives us 3. We should know that our element with 3 protons is lithium. And then we've got an electron neutrino, which is got 0 nucleons and 0 as a proton number. So make sure you know those two decays. They're common. People struggle with electron capture because they forget about the numbers. That's in my experience anyway. So the next thing we're going to focus on today is exchange particles. So during particle interactions, for particles to repel each other, for example, so if we have two electrons and they come together, we know they experience a repulsive force. And that repulsive force is provided by an exchange particle. Now, there are 4 fundamental forces that govern the universe. We've got gravity, weak, electromagnetic, and the strong. This is sometimes a strong nuclear force, but referred to as a strong interaction. This is a weak nuclear force, the weak interaction. So we've got a range of different forces, and they all have different exchange particles. They all act on different things. They all have different ranges, and they all have different roles to govern the universe. So we're going to have a look at these individually and complete this table I have set up. So first of all, an exchange particle is a particle that is going to be exchanged between one particle to another to cause an interaction. You can think of this like chucking a boomerang between two people on boats. If I chuck a boomerang, the conservation of momentum tells us that we'll both move away from each other to conserve momentum. Well, our exchange particle is going to go between the two particles to cause them to move away from each other. So, the exchange particle of gravity is the graviton. No knowledge is required of the graviton in terms of detail, just know it exists. In terms of the weak nuclear force, we have something called a W plus boson and a W minus. For the electromagnetic, we've got the virtual photon. Now, we say it's a virtual photon because we can't detect it as of yet. And then for the strong nuclear force, we have an exchange particle called the gluon. Effectively, the gluon glues the nucleus together. Now, I'm just going to skip down to range because I think that's quite a logical step to think about this. So, gravity. Gravity has an infinite range. It has no endpoint. And you'll look at gravity in A2 physics when you do gravitational fields. We define infinity, and infinity is defined as 0 for gravity. So, it is infinite. Again, our EM force, our electromagnetic force, is also infinite. It can extend way beyond. However, my weak and my strong differ. So my weak interaction does not extend beyond the nucleus. So we looked at this in terms of the graph. We know it's always repulsive. We know as we increase the distance, it gets weaker. Now my strong force that holds my nucleus together doesn't actually extend beyond neighbouring nucleons. So if you think about a proton and a neutron next to each other, it only has that range. And remember, we said that range cuts off about 4 femtometers at a maximum. So for this, it acts between neighbouring nucleons. Now, I'm going to introduce lots of key words here for what it acts on, and these will all become familiar as we move through. So gravity. Gravity acts on anything that has a mass. The force is between two masses. So acts on everything with mass. My EM, electromagnetic, acts on charged particles. My weak nuclear force acts on anything which is quarks and leptons. And then my strong only acts on quarks because it binds them together. Quarks make up a nucleon. Again, more on this in later lessons. Now, the common exam question here is, what interaction is responsible for decay? If you've got an interaction involving normal elements such as plutonium, but you've also got an electron in there, it's going to be the weak nuclear. If it involves leptons, it's going to be weak nuclear. Now, they all have different roles. Now, the role of gravity is to pull objects towards each other. So, pull objects towards each other. Now, gravity ensures that stars and galaxies remain together. It keeps the star intact. The weak nuclear force is responsible for beta decay and fusion. The electromagnetic, its role is to hold atoms and molecules together. And then our strong binds quarks and antiquarks. That's really a summary of the key properties of the fundamental forces. As I say, the universe is governed by these four. You need to know them. You need to know their exchange particles, what they act on, because it will be examined. It's a common exam question, just like the graph I showed you a couple of lessons ago. So the final thing I want to review in this lesson is something called a Feynman diagram. So this is named after Richard Feynman, and it shows particle interactions in space and time. So there's a couple of rules really. So if we have a straight line, that represents the physical particles. What's going on? If we have a wavy line, that represents the exchange particle. It shows the exchange particle moving effectively. Now, we can put axes on these Feynman diagrams, although they're not always present, but the y-axis shows time. So as time moves forward, what is going on? The x-axis shows what is going on in space. Now, I'm going to show you 3 examples of Feynman diagrams today, but you need to know several diagrams. So at this point, I'm going to show you 3, but go to your textbook, go to your notes and just learn them all. So the first one I'm going to show you today is where 2 electrons collide in space. So here I have an electron moving. I have another electron also moving. As these electrons come next to each other, they're going to repel because they've got the same charge, which means as they repel, my electrons will move away from each other. So again, my electrons are moving away from each other. Now we're going to draw in a wavy line to show the exchange particle. Just like that. Now what causes that repulsion? Well, we've just said that if we have charged particles, then the fundamental force is going to be the electromagnetic force. And we said that the exchange particle of the electromagnetic force is the virtual photon. So here you will have a virtual photon. Apologies, I'm not great at drawing the photon. So that's that first interaction. 2 charged particles going to have a virtual photon. At this point, you could draw the interaction responsible for the repulsion between 2 protons. It'll be exactly the same and the same exchange particle. 2 more common examples is what happens in beta plus and beta minus decay. They look a little bit different because there's only one thing on the left side of the equation, for example. So here we've got 2 things. So if we was to represent this as a decay equation, we've got an electron plus an electron is your electron and your electron. We know it doesn't look like that in beta plus or beta minus because we know there's one thing on this side and then 3 on the other. So it's going to look a little bit different. So let's first of all start off with beta minus. So beta minus decay. Again, here's my interaction. Now I'm going to talk in terms of neutrons and protons here, but later on we will talk about quarks. Now we know in beta minus, a neutron changes into a proton. So first of all, we have a neutron. We know that changes into a proton. So a neutron changes into a proton. Now, there's an exchange particle that causes this to happen. So I'm going to put my exchange particle here. It's always at the junction. And we know as my neutron changes into a proton, we get a couple of things going on. We know we have an electron, my beta minus particle, and we know from decay equations we must have an anti-electron neutrino. Now there is convention with particles and antiparticles, but AQA don't test it, but it does exist. Now, what fundamental force is responsible for beta decay? Well, we just said it was the weak nuclear. So we've got a choice. We either have a W plus boson or a W minus. Now, effectively, my neutron is neutrally charged, going to something that is positively charged and forms something negative at the junction. Now, charge needs to be conserved. Well, if I've got a positive and a negative, how am I going to get that positive to that negative? Well, we're actually going to give away, in terms of exchange particles, we're going to give away a W minus boson. And it's going to travel that way. Now, let's have a look at beta plus. Here. So beta plus, I've just said that beta plus, a proton changes into a neutron. So here's my proton. Here's my neutron. Again, we've got a wavy line at the junction because that's where my exchange particle is going to go. And just like before, we have two things here. Well, this time we're going to form a positron and we're going to have an electron neutrino. I feel like beta plus is easy to understand here. I've got a proton and I need to get to a neutron. That means I need to chuck away some positive charge. Well, the way I throw away that positive charge is I give a W plus boson. Like that. So they're Feynman diagrams. They show what's happening in terms of space and time and follow a convention. They're very easy to draw once you know what's going on. Just learn them. Make sure you can draw them. Make sure you can explain why it's that exchange particle. I didn't mention earlier, but this weak interaction also has a Z0 exchange particle, but the AQA specification does not test it. Only the W minus and the W plus. So just a quick review. What have we looked at today? We've looked at Feynman diagrams. We've explained the convention and the rules, and I've shown you beta minus, beta plus, and also an interaction with charged particles. I've given you the four fundamental forces today: gravity, weak, electromagnetic and strong, and we've talked about their exchange particle, what they act on, their range and their role. And also I've introduced you to beta plus decay and electron capture. You've now got 4 interactions for a decaying nucleus that you just need to be able to recall and know.